Hello. Let us first discuss the definition of a vector space. Okay. Before starting the definition, let me just tell you this small note. Vector space is also known as a linear space. In many reference book, you can find the word linear space also. So let us define what is known as a vector space or a linear space. Okay. What is a vector space? A vector space is nothing but a non-empty set. We usually denote it by V. Now, whenever we say a non-empty set, it is not necessary it should be made up of numbers. It could be anything. It could be real numbers, it could be integers, it could be any sequence, it could be any series, it could be functions, it could be power set, it could be anything. But the only thing that we are interested in, it must be non-empty set. If you are given a non-empty set V and you define the operation plus, over here I have used the word define. So this plus does not represent us our usual addition. Okay. So whenever I say I am defining, it means it on me that how I want to define this plus. For an example, I might define 2 plus 3 is equal to 6. So what I am just defining is my plus is nothing but the product. Correct. So we have defined the operation plus. If you have defined the operation plus on a non-empty set, and for every alpha real number and any V bar inside V. Okay, let me just pause this definition for few seconds and let me tell you one thing. The elements of R will be called as a scalars and the elements of V, the non-empty set, will be called as a vectors. Okay, in vectors we are going to preferring it to write as a bars, like the way we use V bar is an element of V. So let us resume the definition. Definition was any scalar alpha inside R and any vector V bar inside V. We define the second operation that is known as a scalar product. By the scalar product, because we are multiplying a vector with a scalar, hence the scalar product alpha V bar. That could be defined in any manner. Correct? Over here also we use the word define. That means it could be in any way you want. So till now what we have, we know that we had a non-empty set with the two operation defined on it. One is denoted by plus and other is a scalar product. If this set with this two operation is satisfying all this 10 condition that we have, 5 condition for addition and the 5 condition for the scalar product, then that set can be called as a vector space over R. Now why the word over R? Since the scalars alpha are coming from the R, hence we say they are the vector space over R. One more note, it is not necessary that vector space R over R only. They might be over rational number, they might be over C, they might be over any field. But at the Fi level, we don't know what is field. Hence, we define vector space over R for our convenience. And the same idea can be generalized for the further fields also. Okay. Now let us define. Till now what we have a non-empty set V with the two operations. This will be called as a vector space over R if it satisfies those 10 conditions, 5 for addition, 5 for the scalar product. Let us just see those conditions in detail. The first condition is, if I consider any two element U bar, V bar from the non-empty set V, and if I apply this operation plus, the new vector that I get should be inside V. Means you are trying to say that the operation plus that you define is closed. Means if I take any two element from the V and if I add them or I apply the operation, the new vector is inside V only. That is known as a binary operation also. Okay. The first condition under addition is the operation is binary. The second condition under that operation is associativity. Means if I want to add U bar, V bar, W bar, and if I add the V bar and W bar first, or if I add U bar and V bar first, my answer is same. In simple word, I can say that I can write the bracket wherever I want. This is the second condition. Okay. Before starting with the third condition, let me discuss something. We all know my 0 is nothing but the additive identity. That means if I give you any number and I tell you to add 0, your answer is the same number. Similarly, we know that 1 is a multiplicative identity. That means if I give you any number and I tell you to write into 1, your answer will be the same. Similarly, whichever non-empty set V has been given to you, there should exist an identity element under that operation. And we usually denote it by 0V because it is working as a 0 for us. Okay, so this vector 0V is such a vector so that if I add it with any other vector, my answer is the same vector. Means there exists an identity under that operation. That is our third condition. That set must have an identity element inside it. Okay, let us see the fourth condition. The way we define the identity, the fourth condition will extend to it. We all know that -2 is an additive inverse of 2. How the answer -2 came? We know that if I add 2 with -2, my answer is going to be the identity under addition. We also know that half is nothing but multiplicative inverse of 2. Since I multiply both of them, I get the identity. So similar idea can be applied over here. What we say that if I give you any element u bar inside V, there should exist an inverse inside V. Means that set should have inverse of each element inside it. Okay, if I give you any element, there should exist another element such that if I apply the operation on them, I should get the identity which we denoted by 0V. Okay, so the fourth condition is existence of the identity. The last is nothing but the commutativity. That means if you add u bar v bar or v bar u bar, your answer is C. The fifth condition is commutativity. Binary, associativity, identity, inverse and commutativity. These are the 5 conditions under addition. Let us see the condition under the scalar product. The similar condition over here is seen in M1 also. M1 means a condition under scalar product. The first condition. The first condition tells us that if I take a scalar product of any two elements, this alpha is any real number and v bar is an element of V, the new vector which is formed, that must be inside V. That means my operation must be closed over here also. Okay, let us see the second condition. The second condition tells us that you can distribute the vectors over the scalar. That means if you have alpha plus beta v bar, that is same as alpha v bar plus beta v bar. Okay, the third condition is almost similar. That tells us that you can even distribute the scalars over the vectors like this. The fourth condition is nothing but like associativity over here. Wherever you want, you can write the bracket. It's like I have alpha beta scalar product with v bar or alpha scalar product with beta v bar. My beta v bar is actually going to be some vector. The last condition is something similar to having an identity. Over here, the last condition is trying to tell us your real number 1 is working as a multiplicative identity. That means my 1 times v bar is same as a v bar. Whatever way you define the scalar product, it might be possible I might define the scalar product as a power, means I might define alpha v bar is same as v bar raised to alpha. So whatever way you define, it must be work as an identity. Means if you apply 1 with v bar, your answer must be v bar only. So any non-empty set V with the 2 operation defined on it, satisfying all this 10 condition, will be known as a vector space or a linear space. Okay. Let us see the first example, which is this. This is nothing but set of all complex number. We know about it. So the set of all complex number will be working as a vector space over R. So we know that what is a vector space? It is nothing but the non-empty set which I gave you. But there should be 2 operations defined on it. And those 2 operations should satisfy the 10 condition given to us. Correct? So I give you the set of all complex numbers, and the operations are nothing but really standard operation. That means if you want to add 2 complex numbers, you have to add it in the usual way. That means if you want to add a plus ib with c plus id, the answer is going to be a plus c plus I times b plus d. That means we are going to add real part with the real part, imaginary part with the imaginary. And the scalar product is also defined in the usual way. Means alpha times a plus ib is nothing but alpha a plus alpha bi. Correct? So with this set and the two operation defined to us, we are supposed to prove it is a vector space. Few conditions are really trivial to prove, but we'll discuss this once. If I add any two complex number, the answer will be complex. Correct? Associativity will be there. What about the third condition? We know that what is a additive identity. The additive identity is nothing but the 0. For any vector I give you, what is an additive inverse? If I give you any complex number a plus ib, inverse is nothing but minus a minus ib. The addition is commutative. If you take any multiple of a complex number, the answer is again a complex number. There is a distributivity, there is associativity, and if you multiply any complex number with the 1, your answer is again the complex. So we can see that the vector space is there, right? You know that this complex number is the thing but a vector space over R. You can easily write those properties. Let us see the second example, which is this. Now our set is nothing but the R2, a non-empty set. The elements are nothing but x, y coordinate, x comma y, where x and y are the real numbers. The addition is defined component wise, and the scalar product is really simple. We just distribute the scalar alpha inside. You can easily see most of the property will get satisfied, but I'm just going to discuss about these two properties. Others are really trivial, I feel. What is nothing but an additive identity in this case? Your 0, 0 will be working as an additive identity, and for any element x, y, the additive inverse is nothing but minus x, minus 1. The same idea of R2 can be extended to the idea of Rn also. Okay? Let us discuss the third example, which is this. So this is nothing but something non-trivial to you guys. So Rx is nothing but set of all polynomial with the variable x and the coefficient coming from the R. So we have a non-empty set. So we should have two operations also. The first operation, addition, is nothing but usual addition of the polynomials. How do you add the polynomials? We add it in the usual way by adding the like terms. Correct? The operation addition is defined in that manner. And the scalar product, that means multiplying with the real number, has been defined in the same trivial way. That means if you have alpha times an x raised to n plus dot 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 plus a1 x plus a naught, then we are just distributing this alpha to each of the term. So this non-empty set Rx with this two operation is going to form a vector space. Let us just see the two important thing. Rest I feel you guys can see. What is a zero element? The zero element is nothing but the zero polynomial. Okay? And for any polynomial given, what is an additive inverse? If I give you a polynomial an x raised to n plus an minus 1 x raised to n minus 1 plus dot 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 plus a naught, what is an additive inverse? You just change sign of each element. Okay? So it will satisfy all of this 10 condition. Hence that set Rx with those two operations will be working as a vector space. So we have discussed the definition of a vector space. We have seen some standard example of the vector space. Obviously without the proof, I feel you can write them. And now I am going to give you some exercise question. There will be two questions, out of which I will discuss one randomly, any out of that, and one will be for you. Okay? Your homework question for today's lecture is this. I hope you like this video. Try to do the exercise questions. We'll meet in the next lecture. If you are new to my channel, please subscribe, share it with your friend. Stay home, stay safe.